everyone. For the next 5 minutes, the four of us are going to talk to you about gravitational lensing, what it is, what causes it, and how we can observe it. As a preface, according to Einstein's theory of relativity, gravity is actually the curvature of space-time as a result of mass. The more massive something is, the more stuff bends, and the mass of a black hole can cause really extreme effects. As a result, when light travels in a straight path through space-time, but the path of space-time itself gets curved, you actually get the effect of bending light. This can be seen in the form of Einstein rings, as shown in this Hubble telescope image.
Lensing can occur when there are two objects that are in line with one another, where one object blocks the other. If we take two light vectors from the unseen source approaching the galaxy or black hole with an angle alpha, and after passing around it, there is a new angle beta that is now greater than the initial angle alpha, which in turn makes the unseen source magnified. Gravitational lensing also allows us to measure the distances to unseen objects, if we know the mass and distance of the lensing object. If we can predict how light will behave in a gravitational field, then we can use that to model the effects of gravitational lensing.
A way to model gravity's effect on photons is to begin with Newton's law of gravity. Here we see the age-old function of gravitational force, where we are given the gravitational constant g multiplied by two masses affecting each other with gravity over the radius squared. Deriving this, we find the gravitational acceleration, which can be utilized to map the curvature of space and time as a directionality of derived force around a mass. Using the idea of deflection of a beta angle, by using the eccentricity and radius of hyperbolic trajectories as well as the photon momentum, which allows photons to follow these hyperbolic trajectories and be deflected to the gravitational force. This is shown here as the hyperbolic trajectory is here, and the alpha angle of deflection is here.
So here we're going to simulate light vectors passing by Sagittarius A*, or the black hole at the center of the Milky Way. We begin with some set of light vectors with angular span of -10 to 10 degrees, with 64 vectors in total. We place the point source at 1 AU behind the object, or the distance from the Sun to Earth equivalently, and a fixed speed of light, which is 300 times 10 to the 6 meters per second. We integrated these positions in velocity vectors as they are accelerated by the black hole, which produces an error of 10 to the -8.
The program that we use to integrate our light vectors as they passed by the black hole is called MATLAB. We used an ordinary differential equation integrator that is built into the program that uses the Runge-Kutta 4-5 integration method. This integration method has some error associated with it that we have predetermined to be on the order of 10 to the -8. So our final results should be within 1/10 billionth of the true value. The differential equation that we integrate is right here. We integrate the acceleration equation that we derived before, that is a function of the mass, the radius, and the direction that the mass is acting on the orbiting object. So these are the results of our simulation. As you can see, we have Sagittarius A* here in the center. And out on the left, we have a point source emitting some set of photons that are passing towards the black hole. This point source comes from 1 AU behind the black hole, and as the light vectors pass, they are bent by some amount. This is the manifestation of that deflection angle beta that we were discussing previously. Moreover, this deflection angle increases as the radius that the light vectors pass the black hole by decreases. You can see that light vectors that pass close are deflected more, while light vectors that pass further away are deflected less. Additionally, light vectors that pass beyond the Schwarzschild radius, the event horizon of the black hole, cease their motion. They do not come back out of the black hole. Behind the black hole, we can see a series of focal points that are generated as different light vectors converge at one point. In reality, there are infinitely many focal points along the axis that the black hole and the point source lie on, but since we have limited number of photons, we only see just a few of them. What's interesting about this is that if an observer stands at any one of these points, they would see our point source of light as a ring that goes around the black hole. As you move further and further away from the black hole, this ring appears to come closer and closer. The angle that these light vectors impact the observer decreases because the beta angle as these light vectors pass is also decreasing.